Hello everyone, welcome to the Frontend System Design interview channel. Today we'll discuss system design of the video streaming service like YouTube or Netflix. Let's begin. Before we begin, let's understand how our application should look like. Let's consider some of the most popular streaming services, for example Hulu, Netflix, and Amazon Prime Video. If you are familiar with any of these services, you can use them as an example for your design. If not, don't be shy to ask the interviewer. The next thing that we have to discuss is what is the difference between streaming service and live streaming service. It is really important to clarify that thing before we start because we have to know what we should design during the interview. Streaming service provides pre-recorded video content on demand. When you watch a movie on a platform like Netflix or a video on YouTube, you are typically streaming video content. Live stream service provides video in real time. This can be anything from live sport events, news broadcasts, video game streaming, and personal vlogs. Before we start to collect requirements, let's ask the interviewer some clarifying questions. First of all, we want to know what parts of the application we have to design, front-end or front-end and back-end part. The answer is we have to design front-end and the API. The next question is, what is the main content on our service? It is video streaming platform like Netflix, therefore the main content is movies and TV shows. Should we support live streaming? The answer is no. What platforms and browsers we have to support? We have to support desktop, mobile, tablets, and all modern browsers. Should our application has offline features? Yes, user can download videos and watch them offline. Should we add a search? Yes, users can search by movie, actors, and genre. What content should we display on the main page? Everything that you think is needed. Should our application be multilingual? It should support English by default, but we may want to add more languages in the future. Okay, now we're ready to discuss functional requirements. Our application will consist of three main components: main page, video player, and search bar. Main page consists promo movie, popular movies, and personal recommendations. Search bar must support search by movies, genres, and actors. Let's discuss non-functional requirements. Our application should support a wide range of devices. UI should look good on different devices and different screens. Performance. Our application should work fast. Accessibility. Accessibility is crucial, and our application should be usable for people with different disabilities. The default language is English, but it should also be prepared to support other languages in the future. Also, we need to focus on protection of video content. And lastly, the application should be able to function offline. Once we have covered these aspects, we need to be sure that we are on the same page with the interviewer. So now it's a good idea to ask them if our list of requirements is fine. Other advice is don't try to include every detail in the requirements. Design interview usually have a time limit of from 40 to 50 minutes. It means that we should focus on the most important or interesting parts of the application. Remember that our goal is not to cover every possible aspect of the application, but to convey the right signals to the interviewer. Okay, let's look at the UI. There are two main UI components, the main page and the search bar. The main page consists of search bar at the top of the page, promotional movie section, and lists of related movies and TV shows. The search component displays search results organized into categories. At the top, there are a list of movies, and below that, a list of actors. Okay, let's move to the high-level architecture. The client side of our application consists of three main parts: UI or view layer, controller, and storage or model. The view layer is responsible for displaying UI components. It includes three primary UI components: main page, search bar, and player. The controller is a core of our application. It manages user events like typing or clicks. It acts as a proxy layer between the model and the view. Data doesn't flow directly to the view from model. Instead, the controller handles data requests from the UI and fetches data from the storage. Also, the controller prepares data for the UI when necessary. For example, it can sort data or filter it. Essentially, the controller serves as a bridge between the view and the model. The API model is distinct from the main controller because it handles requests and responses. It manages endpoints and handles network issues, for example, server errors. The model consists of two storages. Although they might use the same physical space, such as JavaScript memory or local storage, we prefer to separate client state and responses because there are distinct entities. Client state is dynamic and can change during a session, and in contrast, responses are usually cached. We receive them once and keep them immutable throughout the session. Lastly, there is an observer. As we agreed at the beginning of the interview, we will not go deep into backend design. Therefore, we assume that the observer exists and it correctly handles our requests. We discussed main parts of our application. Lastly, we back to the schema again and add more details on it. Next, we have to decide how exactly we will render our application on the page. There are two different approaches: client-side rendering and server-side rendering. When we use client-side rendering, we download the JavaScript file and allow JS to render the whole application. Routing is managed by the JavaScript as well. Client-side rendering application relatively easy to develop and provides smoother transitions between pages because we don't need to load page from the server each time. However, client-side rendering applications have bad time to interactive, especially on the low-performance devices, for example, mobile phones. Also, we have to watch on bundle size, split it on chunks when it's needed. SEO engines don't work very well with client-side rendering, and we have to do some additional works to improve it. Server-side rendering is a more specific approach that is used less frequently than client-side rendering. SSR shines when we need fast initial loading. In this approach, we render a page on the server and send it to the client. Server usually has better performance than user's device, therefore it can render HTML page faster. It is especially important for low-performance devices. SSR applications have good first contentful paint, time to interactive. However, they usually have worse time to first byte, which is not a serious problem for us because the total time of the initial loading is still better. SEO engines work well with server-side rendered pages. However, SSR is not a silver bullet. The main problem is higher costs. It is harder to develop and maintain and require a team with specific skills. Also, server-side rendered applications have slower transitions between pages because we have to load page from the server. In 2 words, SSR is suitable for cases when we need fast initial loading and good SEO. Client-side rendering is good for cases when application has many transactions between pages. We also have a third option, iteration. How it works? Initially, we load static HTML page that was rendered on the server. Then we start to load JavaScript bundle and iterate static HTML with interactivity. adding event handlers. Hydration is a combination of client-side rendering and server-side rendering approaches. It gives us fast initial loading and eliminates slow transitions between pages. However, hydration may create an effect of uncanny valley. It is a state when page was rendered but not interactive. We can improve the situation by using code splitting. Hydration is not perfectly suitable for cases when application has many interactive elements on the page and users expect that all of them will be interactive immediately. In our case, fast initial loading and good SEO is important. Also, we want to provide smooth interactions inside the application. Client-side rendering is not a good choice. Server-side rendering is good enough for the first version of our application, but if we will need to make initial loading faster, we can add hydration in the future. We decided how we render application. So the next topic is how exactly we will receive data from the server. There are two main options, REST API and GraphQL. Let's look at the pros and cons of both approaches. REST API is more flexible. We can construct anything at the top of the REST API. It is also a widely distributed approach, therefore we can easily find developers to work on. However, REST is mostly a set of recommendations rather than a real protocol. Therefore, it's easy to make a bad decision. REST is not scalable enough. Let's imagine the situation when we need to fetch a list of movies with different sets of fields for 3 different clients. For example, we need particular fields for mobile phones and another set of fields for desktop clients. How we should resolve it? Should we resolve 3 endpoints? What if it would be 4 clients or 5 or more? GraphQL can solve our problem. In our application, there are many cases when we need to receive different sets of fields. For example, for the main page, we need only movie poster, name and possibly short description. However, for the movie page, we need more details like director name, actors and long description. GraphQL is perfectly suitable for cases like this, because we can fetch only needed fields from the single endpoint. It significantly improves loading time and decreases load on our server. However, GraphQL doesn't fit for all cases. For more specific operations like authentication and video streaming, we should use classic REST API. Therefore, we have to have 2 API models, one to work with GraphQL and one to work with other services. Of course, supporting both protocols is more expensive and harder to maintain. By the way, real Netflix uses GraphQL as well. The next point is where our GraphQL server should be. We can ask backend team to implement it on the app server. However, it's not the best solution since it makes frontend tightly coupled with a backend, which is not desirable. We expect that frontend will be more flexible, whereas backend is more solid in order to handle business logic. Possible solution here is BFF. BFF is a dedicated server between client and the real backend. We assume that we have only one BFF for all clients, but in the future we can scale it and add dedicated BFF for each type of clients, like desktop or mobile phones. We can use BFF not only as a GraphQL platform, but also for heavy data operations. For instance, we can sort and aggregate data on the BFF and then send this data to the client. We should remember that BFF is a different layer of our application, and it means that it requires their own developing, testing, deployment, and other processes. We have to allocate human resources for that. And therefore, that increased cost of the development and maintaining. Let's look at the data model. We have two main entities. Person, it may be actor or director or scripter or any person that related to the movie, or person may combine this role. And the next entity is movie. Movie can be a movie or a TV show. Also, we have a client state, which has only one field, but in real life it would be much bigger. Also, we have a search result, which contains pagination fields. The next is a samples of GraphQL queries for search, for query movie lists, and movie details. As we can see, we can describe the fields that we want to receive for different types of clients. The next part is details of our application. Here we discuss how exactly we will stream video to the client and how we achieve other non-functional requirements. First, let's discuss how we deliver video to the client. There are two possible options: progressive downloading and streaming. Progressive downloading is a method of delivering content to a user's device that the HTML5 video element uses by default. Progressive downloading is type of streaming. It means that video is downloaded by chunks and it allows users to watch it immediately after the first chunk is downloaded. However, it has two key differences from the real streaming. The video content is stored on the user's device in the browser's cache, and users can jump to a specific video segment. All previous segments must also be downloaded. When we use real streaming, the browser does not store the video in the memory. The video is streamed directly to the user. Again, the difference between progressive downloading and streaming. When we click on stop or start video and we're using progressive downloading, we continue download the video, but it's just stopped on the user's device. When we click stop or start, when we're streaming video, we also stop stream. Okay, what is it better? Progressive downloading or streaming? Each approach has advantages and disadvantages. Progressive downloading is obviously easy to implement because it's default method. However, it doesn't support fast seeking. It means that we can jump to the particular part of the video, and it's not secure because we have to save video on the user's device. From the other side, streaming support jumping. It uses bandwidth effectively because we don't want to download all previous parts of the video if we want jump to the end, for example. It's secure. It supports features like adaptive bitrate streaming. However, it doesn't support offline by default, and it's harder to develop and maintain. And the last point, users can't download video of high quality if its quality is limited by the bandwidth, no matter how long they wait. So what we have to select, progressive downloading or streaming? Let's look at the points that are important for us. First of all, we want to save disk space. We want to make our video secure, and we want to support wide range of devices. Progressive downloading is suitable for small files when bandwidth consumption is not a big issue. It is also easy to use because HTML5 video element uses progressive downloading by default. However, it's not very secure. Streaming is better for large files when we want to adapt video quality to users' bandwidth. Streaming is more secure because it doesn't store video on the user's device. So our choice here is streaming. The next question is, what streaming protocols we should use? There are two main options, HLS or MPEG-. Both are HTTP-based protocols. Let's look at the companies and what protocols do they use. For example, Netflix uses their own Dash-based protocol. YouTube and Amazon Prime Video use HLS and Dash. What is the difference between HLS and MPEG Dash? HLS is a widely supported protocol. It's supported by Safari, Chrome, and Android browsers. MPEG Dash is a modern protocol. It's supported only by Chrome and Edge. HLS supports only limited sets of video and audio codecs, whereas MPEG Dash is codec agnostic. So, what is better for our case? The best choice would be to support both protocols for better compatibility, as YouTube does. For example, if the browser does not support Dash, we can switch to HLS. However, if we don't have enough resources, we can support only HLS, because it provides better browser support. But there is a problem. HLS or Dash will not work with browser by default. The only exception is HLS and iOS system devices. For other devices, we need a MSE, Media Source Extension. Media Source Extension extends the video and audio elements that you can dynamically change for media stream without using plugins. In other words, MSE provides native streaming support for the HTML5 video element without additional browser extensions. MSE browser support is not 100. However, we can use native HTML5 video element and progressive downloading as a fallback. The next topic is ABR, or Adaptive Bitrate Streaming. Adaptive bitrate streaming is a technique used in media delivery to optimize the playback quality based on the viewer network conditions. It dynamically adjusts the bitrate resolution and other video parameters in real time to ensure a smooth and uninterrupted viewing experience. Adaptive bitrate streaming is supported by HLS and MPEG Dash. So it's not different what protocols we will use. Let's look how exactly ABR works. First, the client downloads a manifest file that describes the available stream segments and their respective bit rates. When stream is starting, the client usually requests the segment with lowest bitrate. If the client finds that the network bandwidth is greater than the bitrate of the downloaded segment, then it will request a higher bitrate segment. Later, if the client finds that the network bandwidth is deteriorated, it will request a lower bitrate segment. So, what is the pros and cons of ABR? It provides smooth experience, adapted video quality for each user, regardless of their network conditions, provides smooth playback experience, and also it provides fast start time. However, it's harder to implement and it increases the costs because we need to store and deliver multiple representations of one video file. The next topic is offline mode. Let's discuss how offline mode should look like and what features it should support. Users can download videos and watch them offline. The interface should be available when the user does not have an internet connection. When the user is in offline mode, we should prompt the user to go to the downloaded section. The application should show the current network status. The possible questions here are: how do you protect videos from stealing? What features should be available offline? Where should we store static data and video files? How much video can users upload? Let's try to answer on these questions. The first one, and I think the most important question, is: how do you protect videos from stealing? Videos should be stored on the user's device, therefore they can be stealing. The possible solutions here is to encrypt video content. Video files will be available only for users who have decryption key. Decryption model is built in all modern browsers. It is called Encrypted Media Extension, or EME. Let's look how exactly EME works. EME calls CDM, or Content Decryption Model, that is built into the browser. CDM requests license key from Remote Key Server, DRM, or Digital Rights Management Server. DRM server generates license key, key sent to the client, key passed to the CDM, CDM encrypt meta content, and finally, user has access to the content. The obvious questions here is how user can receive key without internet. We can use persistent license. There are two types of licenses, non-persistent and persistent. Non-persistent licenses are one-time licenses, which are not stored anywhere on a device. They are valid once and then they are gone. Persistent licenses can be stored and can be used multiple times. The disadvantage of persistent licenses is that you cannot revoke them before they expire, so it would be smart to set a limited living time for them, for example 1 week. The next question is how we can make our offline mode workable. For this purpose we can use service workers. Service worker is a client-side server. It works as a proxy between the client and the backend. Service worker is a part of the browser. Here we can determine the current state of the network and get responses from the cache with the cache API if the user has no connection. Where we should store assets. For static file, we can use cache API. It is available in service workers, which is really important for us. For meta content, we can use IndexedDB. IndexedDB is almost a real database with versioning and transactions. It has relatively big capacity, support binary file storing, and has fast asynchronous API. The possible question from the interviewer, why not local storage? Because it has relatively small capacity, it's depending on the browser, it doesn't support binary files, and it has slow synchronous API, so IndexedDB would be a good choice here. And the last question, how much videos users can upload? And it's really depending on the browser storage capacity. We assume that the average size of the media file is from 500 megabytes to 10 gigabytes. We can allocate 100 gigabytes for storing media files by default. It would be enough for storing several movies or episodes of TV shows. Users can manually increase or decrease this value. The next topic that we may discuss is progressive web applications. What is progressive web applications or PWA? Progressive web application is an application built with web technologies. It means that we don't need to know additional languages or technologies. It can work online or offline. We can install it. It has an standalone icon, but it shares process with the browser. In other words, PWA is a kind of browser tab, but outside of the browser. If we want to create a PWA from our application, it must meet several requirements. Sites should use HTTPS. Service workers should be registered to make application works offline. A web manifest should be added to list all information about the site. But what is the problem with PWA? The main problem is browser supporting. For example, on iOS and iPadOS, we can use only in Safari. For macOS, we can use it only with Chrome. However, service workers and offline mode is the hardest part of the PWA. Since we have already implemented it, adding PWA will be almost free for us. The next question is internationalization. Internationalization and localization are very closely related concepts. Localization is a part of internationalization. Internationalization is a process of making application adaptable to different languages and regions. It may include things like localization, translation text content, format dates and numbers, and prepare UI. From the other side, localization may include cultural adaptations and ensure that localized version of the site follows rules, laws, and standards of the region. What is important for us? We have to support multiple languages. We should support Arabic languages, which is left to right directions. And also, we want to support translation management system. We assume that we may not have dedicated team of translators. Therefore, we can use TMS. What is the general recommendations? First of all, we have tried to predict users locale. Next, we should consider difference in word length. Consider text direction, especially for Arabic languages. Avoid string concatenation. Format date and currencies. Do not put text in images because it's not scalable. Or if we need to do that, we have to prepare different versions of image for every language. And the last, we have to use logical properties instead of directions. For example, instead of margin left, we should use margin inline start. The next thing that we can use for internationalization is pseudo-localization. Pseudo-localization is a technique that using for testing localization. It is very useful on the first stage or when we are in the process of adding new translation to the application that does not have it before. With pseudo-localization, we use pseudo language instead of real language. For example, instead of English, we use words like this. It keeps text readable, but highlight problematic places. The next question is how exactly we can translate text on the site. We have two possible options, TMS or translation team. TMS is a translation management system, is a system for automatic translation. Dedicated translation team provides a higher quality of translation. However, it is expensive and probably not suitable for a company that developing only one application. Therefore, we assumed that we would use a TMS. So the next question is what format of translation we should use? There are three possible options: JSON, ICU, and getText. JSON should be well-known web developers. It is easy to write and read. Most popular TMS works with the JSON. However, flexibility makes it not very powerful. ICU message format more powerful and less flexible than JSON. However, it's not supported by major TMS. GetText is an oldest format. It isn't very powerful, but it has good support by TMS. JSON is the best option in our case. It is easy to interact format, and that's supported by all major TMS. The next topic is how we can maintain Arabic languages. First of all, we have to change their attribute. Arabic languages have a right to left direction. Also, we have to maintain text alignment. Change the text alignment to the opposite or use logical properties. Next, we have to rotate decorative and interactive elements. For example, icons should be rotated. Interactive elements, for example, carousels, should change their direction. And also, we should increase font sizes. Arabic characters have more complex glyphs than English characters. In addition, they are usually taller. Therefore, font size and line height should be increased. The next topic is accessibility. There are general recommendations how we can provide good accessibility level. We should use semantic tags. These divs should be focusable, responsive to keyboard events, and have an appropriate role. Also, we have to use area attributes when it's needed. We should use alt attributes for images and hide decorative elements from screen readers. Decorative elements must have the role attribution attribute. Elements with this role will be skipped by the screen reader. The next topic is supporting by a wide range of devices. How we can optimize our application to the phones and tablets. First of all, we should optimize images. We shouldn't load high-resolution images on devices with a small screen. We also should add focus events in addition to the hover events, because hover events is not usable on the mobile screens. Also, all interactive elements should be large enough and it should be usable to fingers. Also, we should change content prioritization. On small screens, we can't afford to show white banners, large decorative elements, and things like that. User experience should be focused on the main content, animations, and complex client-side calculations should be avoided. And the last point is we have to avoid aggressive preloading. Okay, let's see at the performance topics, categorized it by different groups. There are recommendations for network, for images, for video, for CSS, and for JavaScript. Let's look at another detail of the performance that we not discussed before. We assume that on our application we will use carousels, and the question is, should we load all data to the carousel? And the answer is no. Instead of that, we should implement pagination. We should use page-based or cursor-based. And I prefer to use cursor-based pagination here because we don't want to show the user the total number of rows or the current page, for example. Next topic is security. We discussed the video security, and now let's see at the most common vulnerabilities of web applications. First of all, we have to prevent cross-site scripting, and there are recommendations how we can do that. The next thing is cross-site request forgery, clickjacking, and the last recommendation is to use HTTPS. Okay, and conclusion. Let's review how our application satisfies the non-functional requirements. We support a wide range of devices. The video and image quality also adapts to screen size and connection bandwidth, full ELT attributes. Our application is localized. It's secured against major vulnerabilities. Video content is protected with DRM protection. And also, we support offline mode. In offline mode, the app provides a limited set of features, such as watching downloaded movies. We also discussed a PVA that can be used as a replacement for a native mobile app, especially for the first time. Let's take a final look at high-level design. Here we can see everything discussed earlier together and understand how the components interact with each other. The API model now split into two modules, the Auth API and the GraphQL API. In reality, the Auth API model can work with any other REST endpoints. The response cache can now store not only responses, but also media files. We can use an IndexedDB as a persistent storage. Between the application server and the API model, we can find a BFF server that handles GraphQL queries. The download model is responsible for downloading meta content for offline mode, and as we can see, all videos are encrypted. The player components interact with the DRM server to get the license key and play the video content. We have also added service workers and cache API that enable offline operation. We're using the cache API for saving assets. In addition, we're adding a CDN to the schema. In reality, we will use the relational database only for metadata and the CDN server for media files and assets. The stream is also consumed from the CDN to ensure minimal latency. That's all for today. Thank you for watching. If you find this video useful, please don't forget to like it. And if you have any questions, just leave them in the comments. See you next time. Bye bye.